This session, what we're going to do is review briefly chemistry, and this is just to make sure all of you, it may have been some time since you've had your last chemistry class, but all of you have make sure we have some fundamental understanding, because the stuff we're going to discuss about the chemistry is stuff you'll be using in the next 2 or 3 lectures when we get into industrial hygiene chemistry, answering questions regarding various IH formulas and situations that we'll need to do calculations. And by having this fundamental chemistry understanding, we'll make sure that you'll be able to work those problems with no difficulty. So this is just a basic review. Again, chemistry is basically the physical science, which certainly does play a critical role in industrial hygiene and the things we do when we're dealing with hazardous chemicals and hazardous substances. So there are 2 basic types of branches of chemistry, if you will, organic and inorganic, both of them which we have hazardous substances in both groups of those branches of chemistry. If you'll recall, elements are the simplest form that a chemical can be found, and it's made up of atoms. Most of you probably have some access to some periodic table which will give you information about the particular element. At one time there's 106 known elements. I think there might be more than that now with the latest discovery of new chemicals. And if we look at the atom, basically it's composed of a nucleus, and in the nucleus we have protons and neutrons, and those are positive charged protons, and the neutrons are a neutral or no charge. And then around that nucleus we have orbitals which contain electrons, and those electrons are negative in charge. And for an atom to be in a stable condition, you need to have the same number of protons as you do neutrons. And when it's at that equal number, then it's at a happy state, if you will. When you lose an electron from the orbital of the atom, then it'll want to try to do something to regain that void that electron has left, to become a non-reactive types of materials. So here we have just a diagram here showing the atom of beryllium. It's got basically, you can see here 4 protons in the nucleus, 4 electrons around the orbital, and so we have a balanced atom here, and then it has 5 neutrons in that compose the rest of the nucleus. So if we look at an atom, it has a known weight, and it's referred to as its atomic weight of that element, and it's going to be based on the number of protons and neutrons that particular atom contains. And then when we combine 2 elements together, we form what is referred to as a compound, and the simplest or smallest unit of a compound is referred to as a molecule. And here we see examples of a molecule of sodium chloride and a molecule of water, which is hydrogen, or 2 hydrogen and an oxygen. Now, when you combine those atoms, you add the atomic weights of each one of those atoms that are present in that compound, and you'll come up with that particular element or compound's molecular weight. And that's molecular weight's going to be important in a lot of the problems that we work in industrial hygiene, in solving our various problems and figuring out concentrations and so on. So it's important you have that understanding of molecular weight and how it's derived. Now, when we look at the molecular weight, it's the unit of measurement that it's usually found in primarily is going to be gram moles, and it can also be in pound moles. And basically, a gram mole or a pound mole is a mole of water, or a gram mole of water, or a pound mole of water is 18 pounds. And then in each one of those moles that you'll find, we have what is referred to as Avogadro's number, which simply means that there are 6.023 times 10 to the 23rd molecules, or atoms, which can be found in 1 gram mole. Again, something that we'll be using. So we want to look at bonding, how we combine these chemicals together to make up these molecules. And one of the primary ways is a covalent bond. An example of that is a helium gas. The second type is what we refer to as an ionic bond. Covalent bonding, what we're doing is we get the atoms will share a pair of electrons together, where in ionic bonding, the atoms aren't sharing their electrons. What will happen is you'll have one of the elements will have a positive charge, the other will have a negative charge, and as a result of those opposite charges, they'll be able to combine to form that particular compound. So ionic bonding, covalent bonding, 2 forms of causing things to join together to make these molecules. Now, when we have sharing of bonds, we can have 2 bonds or 3 bonds shared together. We refer to that as double bonds or triple bonds. And it just, again, is going to depend on the elements and the makeup of the particular elements that are bonding together. It will depend on how many pairs of electrons that they will share. So let's start by taking a look at some of the fundamentals of inorganic chemistry. And basically, inorganic chemistry can simply be defined as non-carbon containing carbon compounds, or carbon compounds, which will contain some mineral or some other non-organic quality about it. So all of our minerals and things we find like that are going to be inorganic chemicals. Examples are mercury and lead and beryllium and so on. But some of our carbon-containing compounds, which are inorganic, are going to be things like carbon monoxide, carbon dioxide, again, because they don't have those organic qualities that organic chemicals would have. Some of our examples that we find inorganic compounds in our industrial hygiene work are particulates or dust, such as our silica, which is SiO2, that's crystalline silica, or asbestos, which is a fairly complex molecule of a variety of minerals. We got fumes and gases, the nitrous oxide gases, carbon monoxide, ozone, the O3 molecule. In acids are primarily going to be, for the most part, not always, but for the most part, they're going to be an inorganic compound. Some examples here we show are hydrochloric acid and sulfuric acid, 2 very common industrial chemicals. And then we have alkaline materials, or if you remember, acids are those compounds that are going to be, or chemicals that are going to have a pH of less than 7 and on the pH scale. Alkaline materials, sometimes also referred to as bases, are going to have a pH of greater than 7, and then some of our examples of common industrial chemicals which are alkaline are going to be like your sodium hydroxide and potassium hydroxide. More commonly, though, you'll encounter hundreds and hundreds of chemicals that are going to fall under the organic chemical classification. And organic chemicals are basically those that contain the carbon element as its basic body building structure. And that element's going to have characteristics that are very similar to living tissue. The exceptions to that rule, again, are your carbon monoxide, dioxide, carbonates, metal carbonyls. Those are going to be your inorganic. All those other carbon elements, though, are pretty much going to be organic. And some of the common chemical elements that are found or that you're going to find in your chemical substances that you encounter, certainly they're going to have carbon and hydrogen and possibly oxygen, nitrogen, phosphorus, sulfur, chlorine, bromine, iodine. So those are classical chemicals that are can be used to form some of our organic chemicals. So we want to take a look, since there are thousands, literally thousands of chemicals that are organic chemicals, we want to take a little more detailed look into the actual chemistry of these organic compounds. And it's all going to start with the basic carbon element. And the carbon compound is going to have 4 bonding locations to it. And it's going to form a covalent bond where you're going to share these bond locations. And the first example we have here is what we would refer to as a saturated carbon element, where you would have a bond location in 4 spots. And you can see here that we could bond some chemical to each one of those bond locations. And that will form some molecule or compound that we're trying to make and utilize in our chemical formulation. So whenever you see a carbon that has 4 bond locations, one of the terms that you'll see associated with it is called saturated. So if you see something that says a saturated hydrocarbon, you know that the carbon element of it is going to have be 4 bonds with some hydrogen bonded to each one of those bond locations. And so if you put a hydrogen element at each one of the bond locations, then that simplest saturated hydrocarbon that you would form would be methane. So that's a methane compound. And as you add carbons, you can add a string of carbons as much as you want in those saturated hydrocarbons. And the nomenclature then is going to give you an indication of that particular elemental structure. So this is a methane with the 4 hydrocarbons. If we had 2 carbons, it would be an ethane, and 3 hydrocarbons and so on. We'd go up propane to methane, ethane, propane, butane, so on, all the way up to as many carbons as we want. Now, the other illustration we have here is of the unsaturated hydrocarbons. And here again, these carbon compounds here, if the 2 carbon compounds share 2 bonds, then each carbon element's going to want to have 4 total bonds. So we have a location here of adding 2 more elements to this structure to make it in a stable state. Again, if we put hydrogen at each one of those bond locations, that would be the simplest form of this structure. And this would be a molecular structure for ethene, E-N-E, at the ending of it. And then, of course, here we've got the carbon sharing 3 covalent bonds, and so it would have room for a 4th. And again, you could put any element on here. We're just using hydrogen as an example, as a basic hydrocarbon. And these compounds are ethine, or with a Y-N-E on the end of it. So both the double bonds and triple bonds are going to be what we would refer to as unsaturated compounds. And if we're dealing with carbon and hydrogen, they're unsaturated hydrocarbons. So as we'd mentioned, we have over 1 million organic compounds that can be made, and whenever you see hydrogen and carbon composing a portion of those compound structures, they're going to be referred to as hydrocarbons. So anytime you're looking into hazardous substances or hazardous materials and somebody refers to it as a hydrocarbon, you know there are carbon and hydrogen atoms involved in that chemical structure. And the simplest form we have are the aliphatic hydrocarbons. Again, we have our saturated hydrocarbon, which sometimes can be referred to as alkanes, and we get our 2 carbons bonded here. Then we would have room to have the 3 bond locations here. In our simplest form, with just a single carbon, would be methane. With 2 carbons, it's ethane. Then we have propane, butane, hexane, heptane, octane, all the way up our chain. The name will give you, whenever you see methane, you know that's a single carbon compound. Ethane means there's 2 carbons. Propane in the name would indicate that there's 3 carbons, and so on. So that will help you in trying to figure out what a particular chemical is. Then you can have your unsaturated hydrocarbons, as we mentioned, will be your double bonds or triple bonds, and they'll either be your alkenes or your alkynes. And the simplest form of the alkene would be we'd have our 2 bonds on our carbon, and on our alkynes we'd have a single bond. Acetylene is this one here, if we put hydrogen here. Now, one of the characteristics about your double and triple bond elements is they're naturally going to want to get back to a single bond state. And so these compounds are going to have a tendency to be more reactive, wanting to break apart that double bond chain here and that triple bond chain to get back to just a single bond chain that they would find in the alkane state. These compounds are going to be a little more stable than these double and triple bonds that you have going on here. So again, that's just something can help you when we start talking about hazardous substances and their reactivity and so on. Well, another branch of organic chemistry that hundreds, if not thousands, of chemicals are derived from are referred to as aromatic hydrocarbons. And when we talk about aromatic hydrocarbons, it basically is going to be a hydrocarbon with a benzene ring as its primary structure. And at each one of these benzene ring locations here, you can have a bond location. So you'll have 6 bond locations on that benzene ring where you can bond other types of chemicals. If we want to put a methane group on it, we could bond that, and then the rest of these could be something simple as a hydrogen. And this particular structure then is actually the structure for a toluene. Now, if I wanted to add a second methane group on this chemical structure, I can do so. But by adding this, I can put this second structure anywhere on this benzene ring. I can put it in this location, and so on. And so what often you'll see is a numbering system or a nomenclature system that will tell you where you put it. So if you put the structure here, it's on the ring, it's called ortho, O-R-T-H-O. And this would be a meta, and at this location would be para. And so in chemical nomenclature, naming of the chemicals, like for xylene, you'll often see ortho, meta, and para abbreviated just by the initials of xylene. So whenever you see a chemical with the OM or P designation, that's essentially telling you which location the second compound is bonded to. So everything will start off, though, with our benzene ring as our building block. And at each one of the bond locations, we can, just a second, I get this eraser to work. We can add a chemical substance to it. Just skip it. Now, so those are aromatic hydrocarbons. Now you'll also come across reference materials to halogenated hydrocarbons. And what we're talking about here, anytime you see a reference to halogenated hydrocarbons, it essentially means that there's some kind of halogen compound that is bonded to the hydrocarbon structure. And most commonly, that halogen compound is going to be in the form of either chlorine or bromine or iodine. And again, we can further break down our halogenated hydrocarbons into like chlorinated hydrocarbons and further break them down into either an aliphatic chlorinated hydrocarbon or an aromatic chlorinated hydrocarbon. If we're talking about a aliphatic, it's going to be either a straight chain or a branched chain of the hydrocarbons. Here we got some example. This first one, CCl4, that's basically carbon tetrachloride. TCE is going to be trichloroethylene. TCA is trichloroethane. Those are all aliphatic, straight-chained hydrocarbons. But our chlorinated hydrocarbon also can be an aromatic hydrocarbon, and that's just going to mean that we got the benzene ring as our building block. It's often referred to as a phenyl, P-H-E-N-Y-L, phenyl, and you'll see that part of the name in the chemical name. For classical example of a aromatic benzene derived chlorinated hydrocarbon would be PCBs, polychlorinated biphenyl. By looking at that name, just means polychlorinated, means there's multiple chlorine compounds. Biphenyl means there's two phenyl rings, so we're going to have two of these benzene rings joined together, and those chlorine compounds then will be attached to each of those phenyl rings or benzene rings. So those are aromatic chlorinated hydrocarbons. Then we can have chemicals in the organic chemistry family that are alcohols, and basically an alcohol is going to be comprised of a basic unit group, which we refer to as R, and to it is going to be bound an OH molecule. And so anytime you have your basic group with an OH on it, it's going to be some form of alcohol. Again, we can see the simplest example would be methyl alcohol. So we have a methyl group, the CH3, and we bind that together with the OH to form the alcohol. An ethyl alcohol would simply mean is that we've got two of the methyl groups and the OH attached to one of those, and that's going to be ethyl alcohol. Then we have ethers, where we've got not only the first functional unit, but we've also got a second one, and those two are going to be bound together by an oxygen molecule. And those are going to compose our groups of chemicals referred to as ethers. And again, in the nomenclature, we can see here one of the basic structures is methyl ethyl ether, and that simply means to that oxygen molecule on one side we're going to have a methyl group, which is our CH3, and on our other side of the compound we're going to have an ethyl group, which is the C2H5, and that forms that particular chemical compound. So you ought to be seeing here, by knowing some of the nomenclature system, you can kind of figure out what our chemical substances or compounds are going to look at like, and what kind of chemical elements and are being used to comprise those compounds. Then we have aldehydes, and aldehyde is, again, we got our functional group, the R group, and we'll have a hydrogen molecule and a carbon molecule that has a double bond to it. And the basic example of a aldehyde that we show here is we bond two hydrogen elements to the carbon along with the oxygen. Again, if you look, we have our 4 bond locations fulfilled. 1, 2, 3, 4. And this particular compound is the chemical structure for formaldehyde. And then we get into ketones. Ketones are going to be composed of a structure that has 2 functional groups that are going to be bonded to a carbon double bonded oxygen molecule. And the basic example that we show here is the chemical structure for methylethyl ketone, and these are referred to as ketones. And you can see we got our methyl group bound to our carbon, and we've got our oxygen molecule, and to that oxygen molecule we bond an ethyl group, C2H5, and therefore we get our methylethyl ketone substance. Well, you're going to find in organic as well as inorganic chemicals in our industrial work environment are going to be widely used, and a lot of them are used as solvents. So it's important you understand what a solvent is, and a solvent is basically are liquids which have the ability to dissolve other liquids, gases, or solids. So the simplest known solvent that we have is water. But there's a lot of industrial, organic, and inorganic solvents that are also found in the workplace. Now, whenever we're dealing with our inorganic type of solvents, oftentimes they are referred to as aqueous solvents or a water-based solvent. And they're going to usually be in the form of like an acid or an alkaline material or detergents. Some of the characteristics of them chemically are they're going to have very low vapor pressures, which means that they're not going to evaporate easily. And if they don't evaporate easily, they're not going to build up into the air that we breathe in a high concentration. So as a result of this, aqueous solvents will traditionally not be a big inhalation hazard for us, but on the other hand, they can be a fairly severe skin contact and irritant to the body if the body comes into contact with them, because they are oftentimes an alkaline or an acid-based kind of material. Then a much broader area of solvents that we find are organic solvents. And the organic solvent is going to be basically any solvent that's going to be made up from organic chemicals. And they're widely used, and they're very effective cleaning. And but because of their organic makeup, you will find that the organic solvents will evaporate much easier and therefore become more of an inhalation hazard to us. They can also be a skin hazard, but they evaporate easy, and as a result of that, they'll have higher vapor pressures, and they'll get into the air easier to where they become an inhalation problem to us. So there's a trade-off. So the aqueous solvents are perhaps a more dangerous to us from a skin contact, an eye contact, versus the organic solvents. But the organic solvents are more of a inhalation kind of problem, as well as, depending on the chemical makeup, can be more of a fire hazard to us as well. Well, we started last, when we talked in toxicology about the different states of matter. And basically, if we again look back, our 3 basic states of matter that a chemical is going to be found is going to be either a solid, a liquid, or a gas. And to define those 3 states of matter, a solid is simply a substance that has a definite shape and volume. And you can see it, and it's not going to change. A liquid, on the other hand, is what we would call a formless fluid, which takes the shape of the container it's in. So the liquid in this bottle, you can see it's going to take the shape of the container. Change the container, it's going to have a different shape. And then you have gases, are basically formless fluids which uniformly distribute themselves throughout the container it's contained in. The simplest illustration of gases are the air in the room that you're currently sitting in. That air is composed of oxygen, nitrogen, and a variety of inert gases, low level of inert gases. And those gases evenly distribute throughout this room. There's just as much of those of the gases over here as there are on the other side of the room. They're basically of low density and viscosity, and they're going to be evenly distributed. In industrial hygiene, we kind of expand on those states of matter to use some more defining terms for substances that we find in the work environment. We still use gases, still has the same definition, formless fluid uniformly distributing itself throughout a container. But then you have vapors, which vapors are going to be typically at room temperature and pressure, they're going to be either a solid or a liquid. But when you change either the temperature or the pressure, then it can be transformed into a gaseous form. And it'll be just like the molecules of gas in air. These chemical substances can evaporate off and form these gaseous materials, which we refer to those as vapors. Now, if we change the temperature or the pressure back to the typical room temperature pressure, then those vapors are going to, again, transition back into either that solid or liquid form. And then we have fumes. The term fumes, as we mentioned before, are actually solid particles that are formed from a volatile solid which condenses in air. So if you can imagine taking a piece of steel or metal of some type and applying high temperatures to it, and if you looked at it under like a welder's helmet, you would see that metal melt and it would form a liquid, and as that temperature continues, that liquid would get hot enough that it would vaporize or evaporate off, and it would evaporate off that pool of melted metal. And when it evaporates, though, it hits the cool air, and that vapor then, that molecule condenses within air and solidifies, and it forms a solid particle. Now, that particular particle that is formed is very small in size. Basically, the size is going to be about 1 micron in size or less, 1 micron. Remember that a micron, 10 microns are sizes of particles that can get into our respiratory tract system. 5 microns can get into the deepest region. So we're talking about very, very small size particles that can clearly get down in the deepest region of our respiratory tract system. To try to, again, put it in other perspective, the smallest size particle that you can see with the naked eye is going to be about 100 microns in size. And with the aid of a light shining and you see a haze of particles floating around in air, those sizes that you can see with the aid of a light are going to be about 50 microns. So we're talking something that is so small that they can be present in an abundance and you not even be aware that they are present because we can't see them. Then we have the term dust, and dusts are solid particles which are created by some mechanical action, usually a grinding or a crushing or pulverizing a solid material. And this mechanical action is done to such a degree that it can make these particles, these dust particles, so small they can be respirable in size. In other words, 10 microns or less. And as a result of that, those are the ones that are going to have a potential of getting into our respiratory tract system, into the deepest regions of the lung. So the dust that you can see blowing out in a dust storm, again, those size particles are very large. They're probably close to the 100 micron size range. We're talking about being most concerned about those that can get into the respiratory tract system, which is going to be 10 microns in size or less. And then we have mists, which is an aerosol where we break liquid droplets, a liquid down by, again, oftentimes some mechanical action, like spraying it or forcing it through nozzles, and it breaks that liquid down. Spray painting is a great example of where we find chemicals that come in the form of a mist. So we're breaking those liquid particles down, again, putting them in a size that can get into the respiratory tract system. Well, when we're talking about hazardous chemicals, or chemicals in nature, we're talking about these chemicals that can get out into the air in the form of a gas and a vapor. And basically, those gaseous materials are going to behave in accordance with our basic gas laws. And here is just the illustration of the gas laws. And you'll need to become familiar with these because you'll be using these in many of the problems that you encounter in your projects and on the exam. But basically, the mathematical relationship of gases states that an ideal gas is going to behave in accordance with the formula you see up here. Its pressure and the volume of that gas is going to equal to the number of moles of that gas times a gas constant, and which is a unitless dimension, and temperature. And so P is pressure in millimeters of mercury, where T is our temperature, and in this equation it's used as the absolute temperature in Kelvin. And the volume is going to usually be expressed in cubic meters. So given the ideal gas law, we can express that in different ways, and here's a couple of examples of how it can be expressed. P1 over V1 divided by T1 of the particular gas is going to equal of that gas of P2, V2, and T2. In other words, we can change the conditions and the conditions we can change of that gas is going to be the pressure and the temperature. And by changing the pressure and the temperature, it's going to change the volume that gas will occupy in a space. So if we want to manipulate this formula around, we can see here, we can manipulate it and say that the volume of a particular gas, V1, over the volume of that gas in a second state is going to equal to T1 over P2 divided by T2 over P1. So these conditions are basically expressed in the standard temperature and pressure conditions. So basically, the volume of the gas is going to be proportional or inversely proportional sometimes, either proportional to the temperature change and inversely proportional to the pressure changes. Well, we talked about molecular weight, and another term that you will use is a mole of a compound. And moles are basically a ratio of the weight of a molecule to the weight of water. And 1 gram mole of water is equivalent to 18 grams of water. So the weight of water in grams is equivalent to the water's molecular weight. If you looked at the structure, we remember that water is composed of two hydrogen molecules, which have an atomic weight of 1 each, and the oxygen molecule, which has an atomic weight of 16. So if we add those up, those atomic weights up, we get the molecular weight of water of 18. So 1 gram mole of water is 18 grams of water. And this is going to be important to you, again, using this molecular weight concept in some of the calculations we get into. Well, we talked about expressions of concentrations, and one of them that we frequently see is parts per million. Now, you can express parts per million either by weight or by volume. And oftentimes in your environmental work, when you're doing soil samples or water samples, you're going to see the reference of parts per million. That reference is going to usually refer to the parts per million by weight of a material. And the parts per million by weight is defined as the parts of the solute per million parts of the solution. Put in simpler terms, it's the parts of the chemical you're interested in per million parts of the solution it's found in, oftentimes water or soil or whatever. So 1 part per million is also approximately equal to 1 milligram of that chemical per milliliter of solution. Milligrams per milliliter. Now, we use the expression of parts per million by volume when we're talking about air concentrations. And the air concentration part per million is the volume of gas or vapor compared to the volume of air in that mixture. So if we had 10 parts per million of carbon monoxide, we would have 10 parts per million and a million parts per million of air. And so now we can express that part per million formula is equal to the volume of the gas divided by the volume of air times a million, and that's how we would derive a parts per million by volume. Well, you can remember how we can also express those gases and vapors in using the terms milligrams per cubic meter. And milligrams per cubic meter, to be able to express that, is simply based on this formula of a part per million times its molecular weight is going to equal milligrams per cubic meter times 24.45, and that is at a normal temperature and pressure of 77 degrees Fahrenheit and the barometric pressure at 29.92 inches of mercury. To be able to help figure out the setup of this formula, just think of there's 2 M's in the terms, the molecular weight on one side and the milligrams per cubic meter on the other. Now, that formula can change, but down to 24.1 if we change the temperature and pressure from normal temperature and pressure conditions to standard temperature and pressure conditions, which we're modifying. The thing that changes there is our temperature goes from 77 degrees Fahrenheit to 70 degrees Fahrenheit. Well, if you plug it into your formula and your pressure, the ideal gas laws, you would see this constant change from 24.45 to 24.1. Most of the time, I believe for most of our problems, you're going to start with this formula of using the formula with a constant 24.45, which is the ideal, the gas law setup. Well, we want to take a look at units of measurement and make sure we all understand the metric system again, because we're going to use these terms in our units of measurement. So whenever we refer to as micro, we want to remember a micro is equivalent to 1/1,000,000th of something. And if we're talking about it in volume, it could be microliters. If we're talking about it in weight, It could be micrograms. Oftentimes when we're referring to micrograms, we also refer to as microns. Then we have milli, and anytime we're dealing with milli in our metric unit, it's 1,000th of the unit of measure. And again, by volume it would be milliliter, by mass it would be milligram. And then we could also see centi, which refers to 1/100th of the unit, and centimeter is a good illustration. And then we could have kilo, and kilo is 1,000 times the unit of measurement. So if we have 1,000 grams, that equals basically 1 kilogram. Now, some of our units that we see in length that are used are going to be 1 meter is going to be equivalent to 3.28 feet or 39.97 inches. So when we're talking about a micrometer, could be a micron, as we mentioned, and you can see here a micron is going to be equivalent to 1/1,000,000th of the dimension for an inch, or 0.0003937 inches, really small. 1 millimeter, you can see, is going to be 1/1000th of the 39.37 inches, and 1 centimeter is 1/100th of the inches, or 0.3937 inches. When we look at volume, again, 1 liter is going to be equivalent to 1,000 cubic centimeters, or we abbreviate it as cc. So anytime we have 1,000 cc's, that's going to equal 1 liter. 1 cc is also going to be equivalent to 1 milliliter. And 1 milliliter equals 0.0338 fluid ounces. And then we have finally 1,000 liters, and there's 1,000 liters in 1 cubic meter. We'll use this when we get into doing our calculations involving volumes of material and rooms and so on. And then finally we have the units of measurements for gases, or for mass, I'm sorry. And for mass, the unit of measurement, we start off with 1 gram. And 1 gram essentially is equivalent to 1/1000th the weight of 1 liter of water. So 1 milligram, again, is going to be 1/1,000,000th of a gram. Its abbreviation is mu, the UG. 1 milligram, which is mg, is going to be essentially 1/1000th of a gram. And then we have 1 kilogram, which is going to equal 1,000 grams. So that basically gives us a quick overview of chemistry. In the next session, we're going to get into talking about industrial hygiene chemistry problems, where we're going to use this information in solving some everyday problems or issues that we encounter in the industrial workplace. And then we'll have a project that will be associated with both this lecture and the next lecture that will contain a number of problems for you to start solving using this information. So that'll end this session, and we'll see you again on the next session on industrial hygiene chemistry.